AP Calculus BC, Unit 9, Day 2, warm-up and lesson. So warm-up is just some practice from yesterday's assignment. Does the series converge? We have a couple tests that you could try. These are both number series, right? These are both number series. We have two tests as of now. We have the Nth Term Test, which says if the limit as n goes to infinity of the nth term needs to go to 0. If it doesn't, it diverges. It's a test for divergence. This on its own is inconclusive. If it's something other than 0, it diverges for sure. And then we have the ratio test, which says the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term should be less than 1. So go and try these, pause the video and try these on your own. Okay, assuming that you tried these, I'm going to try the nth term test first. And in your work and on your test and things like that, I want you to name the test and very clearly show the proper work. Now, this would go to infinity over infinity, but factorials beat any kind of exponential, so it does go to 0, but that is inconclusive. So we're going to try the ratio test. And so we're going to write the limit as n goes to infinity of the absolute value of the 10 to the n plus 1 power over n plus 1 in parentheses factorial divided by the nth term or multiplied by the reciprocal. We can clean it up, simplify it before taking the limit. So rules of exponents are often helpful. Factorial tricks. N plus 1 factorial is n plus 1 times n factorial. So this is what we have now. And it goes to 0, which is less than 1. So it converges by the ratio test. Okay, next one. Nth term test. Limit as n goes to infinity of n over 3n plus 1, which is going to be infinity over infinity. These are the DOM terms. They grow at the same rate. They're the same size relative to each other. The answer is 1/3, which is not equal to 0, which means it diverges. This is what I want you to write. I want you to write doesn't equal 0. That's the criteria that we're judging that against. Okay, so in this scenario, that would have been fast. Now let's try it with the ratio test also. I recommend right now trying every possible test that is appropriate to be applied to a problem just to get good at all of them, because sometimes one works and sometimes another works. So limit is the absolute value of n plus 1 over, now we plug n plus 1 in here and the 3 gets distributed to it. So it's 3n plus 4 because there was a plus 1 already. And we can't simplify this at all, but these guys are going to give you 1. These guys are going to give you 3 over 3, which is 1. You're going to get 1, which is inconclusive. Another reason to try the nth term first is that your ratio test might not tell you the answer. So, okay, so we should be getting good at that. Now we're going to add some stuff to our list. So we have the nth term test. Its successive terms must approach 0. In words, if not, the series diverges. It's a test for divergence. It's necessary but not sufficient. So, for instance, a harmonic series passes the nth term test but diverges, right? So a harmonic series, by the way, which is a very famous series that we're going to be seeing a lot of, is just 1 over n. So it's 1 plus 1/2 plus 1/3 plus 1/4. And if you take the limit as n goes to infinity of 1 over n, it equals 0. But it diverges. It's getting smaller. It's going to 0, but not fast enough. Okay, now there's another test called the comparison test, which is like your last resort test. okay, because it is generally, it's not super straightforward. So we really only use it if we can't use something else, okay? The idea is pretty understandable. It's the execution of it that's hard. It says if you have a series where every term in the series, okay, so we're comparing these two, okay? They're saying if this series converges and all the corresponding terms in this series are smaller than that series, well, then this one has to converge too. So if this one converges, doesn't blow up, and this one's smaller than it everywhere, then it has to converge. And it doesn't have to be smaller than it everywhere. It says for all n greater than n, starting at some point. So the first terms don't have to obey it, but long run it has to obey it. And I think that totally makes sense. If this series converges and I can fit this one underneath it smaller than it, then it's got to converge. The same idea, if this one diverges and then all the terms in this other series are bigger than this, all the corresponding terms starting at some point, then this guy's got to diverge too. So if you can fit this one underneath this one and it converges, it converges. If this one blows up and this one's bigger than it, then it's going to blow up too. So the idea totally makes sense. The execution of it's kind of hard. There's another idea called absolute convergence. And what it says is if you force a series to be all positive and it converges, then its original version has to converge also. Okay? So the only possibility is of this is going to be smaller than this because it might have some positive negative terms. Okay, so for instance, like an alternating series, which we see a lot of, and we will see a lot more. If some terms are negative, then they cancel with some of the positive, right? You know, so we're saying if this one converges, then if we had one of those ones that like went back and forth like this, well, it's if you take this and you force them to all be positive and that converges, well, then the original one has to converge too. Okay. So we call it absolute convergence. Sometimes we do that because some of the tests I'm going to teach you how to use require all the terms to be positive to use it. And so we kind of like this is like worst case scenario, right? If they're all positive, then they're going to add up and more likely blow up. If some are positive, some are negative, they kind of cancel each other out and they actually converges faster. So now we can apply this idea to other series that aren't exactly alternating but have positive and negative terms. Now, this is sort of a summary of what we talked about last time, with the possible outcomes of a power series. They either never converge and just always diverge. You just say it diverges for a power series. It converges a single point, the center. It converges on an interval, open or closed. Like for instance, this is a series that we studied, a power series we studied last unit, and its interval of convergence was that. And then we studied this one also, and it had an interval of convergence where one of the ends actually worked. And so we're going to have to test the endpoints on our own as number series. It could converge for all possible reals, and we've studied a few functions that power series who converge for all real values. So let's do some examples on the back. We try the ratio test again. Might throw the, I mean, that's just one that you should get. It's pretty straightforward, but it can get messy. So, you know, the ratio test is the limit as n goes to infinity of the n plus 1 term divided by the n term, and it has to be less than 1. For geometric series, this gives you the R value, which is what we've been using. So this problem here, now what we can do is we can say limit. We can try the nth term test. let's see, nth term test, which I can already tell it passes. You should get to a point where you can just look at nth term test. Oh, it passes or fails. And if it fails, you write it down. If it passes, you don't bother. So this isn't going to go to 0, but that's inconclusive. Okay. Now, these are number series, which means they have no x's in them. So the answer is either converge, diverge, or possibly inconclusive. Okay, absolute value of 1 over n plus 1 to the square root of the n plus 1 times n square root of n. Okay, we could rewrite this and sort of line things up that are more like each other. Like we could put the n over the n plus 1 together, and then we could put the square root of the n over the n plus 1 together. Now, if we take this, it's going to be infinity over infinity, but it's going to be 1. This one's going to be infinity over infinity, which is going to be 1. Square root of 1 is 1. We're going to get 1, which is actually inconclusive. So we're starting to see some issues here, okay, that this is one that we can't find the answer of. It's inconclusive. So if we're on the homework, I guess you just say inconclusive, but what's going to really happen is we're going to come up with some other tests and series to be able to show. In fact, we could use the comparison test, which I'm going to show you later, except that we need another test to compare it to. Okay, next one. We could try nth term test. So that last one, we don't know if it converges or not. Based off of 2 tests, we don't know. Now, e to the n is going to go faster than n, so it's going to go to 0, but that's inconclusive. So we're going to try the ratio test. This is another number series. So we can take the limit as n goes to infinity, absolute value of n plus 1 over e to the n plus 1 divided by the previous term or multiplied by the reciprocal. And rules of exponents, we could rewrite it. This would be sort of the nicest way to present it. You could rewrite it, put the n plus 1 over the n times 1 over e. Now, these can go infinity over infinity. It's going to be 1. So what we get is we just get 1 over e. Is that less than 1? Yes. So it converges by the ratio test. Now, the next one is power series. So it's more likely we could get that it always converges or always diverges, but more likely we're going to get an interval of where it converges, an interval of convergence. So that's usually what you're looking for, interval of convergence. And maybe even the radius of convergence. That might be a question. Now, we could try the nth term test, but it's it's unlikely that's going to give you any information because it really probably depends on what the value of x is. So we're usually going to jump straight into the ratio test for power series. So we can take the limit as n goes to infinity, absolute value n plus 1 squared x plus 3 to the n plus 1 over 5 to the n plus 1 divided by the previous term multiplied by the reciprocal. And then let's try and clean this up. So we can do a lot. So I'd rewrite this as limit as n goes to infinity of absolute value of n plus 1 over n squared times x plus 3 over 5. Now, this is going to go to 1. So we're going to get the absolute value of x plus 3 over 5 needs to be less than 1. So that's how we're going to find our interval of convergence. Now, if you want the radius of convergence, or even if you just want to solve this, you can multiply both sides by 5. That's your radius of convergence. And your center is the thing that makes this 0. It's centered at x equals negative 3. So you could do that, or you could just start solving it, multiply everything by 5. So that's the interval of convergence. The radius of convergence is 5. Now, this isn't actually necessarily an interval of convergence, so you still would, we haven't done this much yet, you'd still have to test the endpoints, each on their own. So you would say, okay, well, I'm going to test x equals negative 8. And you're going to plug it into the original power series and get a number series. You replace the 8 with negative, the x with negative 8. So then you get n squared negative 1, negative 5 to the n power over 5 to the n. If you try and clean this up, it's going to be n squared over times negative 1 to the n, right? So this is an alternating series. Problem is the terms get bigger and bigger and bigger. So if you were to do the nth term test, limit as n goes to infinity of negative 1 to the n squared, you're going to get positive negative infinity, which isn't equal to 0, so it diverges. So that n diverges. So then you have to do x equals 2. And get n squared, 5 squared over 5 squared. And you just get n squared. And same thing here. So nth term test, limit as n goes to infinity of n squared is going to be infinity, which isn't equal to 0, which means it diverges. So neither n works. So this is our final interval of convergence. We're not going to have any brackets or include the n's. But this is the work you're going to have to do. AP test, my test, you're going to have to test the endpoints for power series. Okay, but we also probably need to learn some other tests. We were able to pull it off this time. Okay, now here's an example of using the comparison test and also the idea of absolute convergence. This on its own, if n equals 0, and we're going to blow up, we could try the nth term test. Let's see, limit as n goes to infinity of sine x, the n over n squared. It's going to go to 0, but that's inconclusive. We could try the ratio test. Now, one of these might work. I'm going to still show you this comparison test. Okay, so I don't know what's going to happen here. I actually didn't do this before. Let's see. So rules of exponents, factorial stuff. So this is going to be limit as n goes to infinity of absolute value of sine x over n plus 1, which equals 0, right? Which means and this is a power series, but it converges all the time for all reals. So usually we're trying to find an interval of convergence, so we're going to say negative infinity to positive infinity. Now, I want to show you a different approach, just in case this didn't work or whatever. So I mean, this would have been our best choice here. But here's the idea: we know that sine x has to be between or equal to negative 1 and 1, right? Minimum of negative 1, maximum of positive 1 for sure. So we can use that to help us. We say, okay, well, all right, well, the series n equals 0 to infinity of sine x, the nth power over n factorial, if we, and this is another thing, absolute, if we take the absolute value, well, now we know it's between 0 and 1. We know that this is going to be smaller than Worst case scenario is there's a 1 on top, right? So this is a comparison test. I'm saying this is for sure smaller than this. Now the goal, and this is the hard part, is to find a series that you know converges. Okay. Now this happens to be a series that I know it converges to E. It actually equals E. And this is just, usually we're not trying to figure out what it converges to. And by the way, because this one converges to E doesn't mean this one does. This one we know is actually smaller than that. Now, how do we know? Well, this is a famous power series, Maclaurin series that we were studying last unit. It's the same thing as x to the n over n factorial, which is the power series for e to the x. If you remember that pattern, right? E to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial, right? That's what this would give you. And ours is that with x equal to 1. So that's how I know this equals e. But here's, that was just a little bit of extra stuff there. But here's the deal. We know that this converges because we know that converges, and this one's smaller than it. So you got to somehow pick one that's smaller. And this isn't, this is kind of a hard thing, and I'll kind of show you more examples as the unit goes on. But we know that now this isn't exactly the series that we were trying to work with originally, but we know that this one converges by the comparison test. The one with absolute values around it is the one that we were able to more directly compare to this. But because the one with absolute values converges, then we know that this one, which is going to have positive and negative terms, the original one's going to have positive and negative terms. Well, if you force them to all be positive and it converges, then the original one is going to converge. And we actually say it converges absolutely. So it's kind of a stronger convergence. We could just say it converges. But if you force all the terms to be positive and it still converges, then we say it converges absolutely. Anyways, just some new terms to throw in there. Today's assignment, try these problems. You need to get practice with these. We are going to have to learn several more tests, convergence tests. So that's it. Try the problems, check your odds in the back of the book, check your evens online.